Thank you very much, and it's nice to be here at Todmorden in person rather than purely virtually via Zoom. So yes, this is the end of everything. I'm going to tell you about the fate of the Earth, the fate of the Sun, and the fate of the universe a long, long, long way into the future. And so as not to finish on a totally depressing note, I'll have a little epilogue which hopefully brightens things up a little bit. So if you'll forgive me paraphrasing our friend Buzz Lightyear, what we're going to do this afternoon is go to eternity and beyond. So I'll be giving a little bit of an introduction, and along the way, in the next 3 or 4 hours, however long I take, I'm going to be talking about the future of what's going to happen to the Earth, the far, far, far future of what's going to happen to stars like our Sun and other stars in the galaxy, and then I'll be looking to the far, 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 far future to ask what's going to happen ultimately to the rest of the universe. And then I will wrap up on a slightly more upbeat note to make sure you're not all thoroughly depressed. So, as was just mentioned, a few months back I gave you the beginning of everything. I'm not going to recap that, but just to remind you that the universe was made in approximately 3 minutes. That's how long it took after the Big Bang to make all of the hydrogen which is powering all of the stars that we can see in the universe. We know the universe is expanding, that's an observational fact, and so we deduce that if it's expanding, everything used to be a lot closer together. And if we wind the clock back far enough, we can deduce that everything that we can currently see in the entire observable universe used to be only a few centimeters apart. Basically all crushed into something the size of a golf ball. That takes a little bit of imagination to figure out how on earth that can be, but as far as we can tell, that's how the universe began. 13.8 billion years later, we find ourselves where we are now. And this afternoon's talk is not about the past and where the universe came from, it's about how things are going to change in the future. And to try and keep tabs on where we are, because otherwise it gets very confusing. If we talk about millions of years from now, or billions of years, or trillions of years, it does get confusing. On describing how the universe began, we're always talking about a fraction of a second. But here, we're talking about millions, billions, or trillions of years into the future. So to try and keep tabs, there's this number line along the top there. And a red rectangle is going to move along that top as we go further and further into the future. Each box is 10 times further into the future than the previous box. So for instance, that box represents 1,000 years into the future. And if we keep on going, that's 1,000,000 years into the future. And if we keep on going, that's 1,000,000,000 years into the future, and so on, 1,000,000,000,000 years into the future. So as we go along, the red box allows us to sort of keep track, if you like, of where we are. And just a plug to make it clear, I've used a particular publication. We don't need to worry about the date and the journal, but I've used a publication talking about how things might change in the future regarding stars and galaxies. I've used that to try and keep all my slides in the right order. So we're not going to start next year or 100 years from now. We're going to start thousands of years into the future. Let's assume that we get climate change under control. Let's assume we don't have World War III. Let's assume that we can go a few thousand years into the future. We know the Earth is rotating and the axis points to a particular point on the sky. Because of the interaction of the Earth with various other planets and the Sun, the direction that the Earth's axis points is tracing out a big circle on the sky. And the place where the Earth's axis point gives us the North Star. So at the moment, the North Star is the star we call Polaris, over here on the right-hand side. But in 10,000 years, the Earth's axis will have precessed, it will be changing direction, and it will be pointing at a different part of the sky. It'll be pointing close to the very bright star called Vega. That is a very bright star. It's one of the brightest stars in the sky. So one of the consequences of the pole star changing is that it's going to be a lot easier for Boy Scouts to be able to point out that way is north when asked to do so. At the moment, they have to find Polaris, which is not particularly bright. In the future, they'll be able to use the bright star Vega. But also, there are other changes. At the moment, The closest approach from Earth to the Sun, because the Earth goes round the Sun in an ellipse, not a circle, the closest approach of the Earth to the Sun occurs in northern winter, when the axis is pointing away from the Sun. Whereas when the pole changes, in another 10,000 years or so, we'll be closer to the Sun during northern summer, which means the seasons will be a bit more exaggerated. Nothing to do with climate change that's man-made. This is a natural consequence of the way things change because of spin and because of orbit. And there are a number of these variations in the Earth's climate that are due to the way the Earth is spinning or the way the Earth's going around the Sun. These are all collectively called Milankovitch cycles. They simply mean the Earth's climate will change because of changes to the way the Earth spins and the way the Earth moves. We'll come back to that shortly. We're now looking at 10 to the 5 years into the future, 100,000 years into the future. If you remember the Voyager space probes launched in the 1970s, they are now leaving the solar system. They were launched back in the 70s. Voyager 1 went past Jupiter and Saturn. Voyager 2 went past Jupiter, Saturn, Uranus, and Neptune. And both are now leaving the solar system. And we can tell which way they're going, and we know how fast they're going, so we can work out when they next go through another solar system. So Voyager 1 at the top there is heading off towards the star system called Gliese 445. And Voyager 2 down at the bottom is heading off in the direction of another star system called Ross 248. So these ambassadors, if you like, from our solar system will be going through other solar systems on this sort of timescale. The Pioneer probes were launched a few years earlier than Voyager, but they're moving more slowly, so they'll take a little longer to get anywhere. Pioneer 10 is heading off towards the star Aldebaran, for anybody who knows their constellations, and Pioneer 11 is heading off in the direction of the center of the galaxy. Still on a timescale of 10 to the 5 years or so, we know that ice ages come and go on periods, on cycles of 100,000 years. We know that from the fossil records, effectively. And given that we entered a warm phase about 100,000 years ago, that means the next ice age is due on approximately this scale. So we can say with some confidence there will be another ice age in the future on a time scale of about 100,000 years. It's not absolutely regular as clockwork, but this is another manifestation of the so-called Milankovitch cycles. It's a result of how Earth is orbiting the Sun and how that orbit, that elliptical orbit, changes slowly over time. We know that the spin of the Earth is slowing down. The Earth takes 24 hours to rotate once, but only approximately 24 hours. We've been, with atomic clocks, monitoring the rotation rate of the Earth for many, many decades, and we've seen that it's been changing. For quite a few years, quite a few decades, we've been adding a leap second every once in a while, once every few years, to keep our clocks synchronized with the rotation of the Earth. But because the Earth is slowing down, the rate at which we have to insert leap seconds into the clocks keeps changing. And it's been calculated that in 10 to the 5 years, we'll have to introduce a leap second, not once every few years, but once every day. In other words, the length of the day will no longer be 24 hours, it'll be 24 hours and a second. And so we'll have to keep adding a second to keep our clocks synchronized with the rotation of the Earth. The Earth will continue to slow down. It's slowing down because the moon is generating tides, and those are slowing the Earth's rotation down. And we'll see a little later, the Earth will slow down even more. Some stars are going to die. It's difficult to tell when. Most stars live for billions of years, but some of them, the most massive ones, don't live for quite as long. And we know that some stars, for instance this one called Eta Carinae, is probably getting towards the end of its life. It's swelling up, and part of its outer atmosphere has been blown off to produce this nebula, this cocoon-like structure that we see here in an image from the Hubble Space Telescope. This is a sign that it's getting very stable and very old and possibly going to go supernova at some point. Supernova is what happens when a massive star collapses and an enormous amount of energy is released. We can't tell when it's going to happen, but we do know it's going to happen on this sort of time scale. Another star, the top left-hand corner of the constellation of Orion, that star called Betelgeuse, that's going to go supernova as well on this sort of timescale. We can't say exactly when, but we think on a timescale of 100,000 years, this star will also go supernova. And that's an artist's impression of what it will look like. That star will be so bright, it'll not only destroy the constellation of Orion, it'll be so bright that particular star will be visible during the day. So we'll have two suns in the sky for a little while. There will be other changes because we are in a galaxy and we're going round the center of the galaxy along with all of the other stars. Essentially, every star is independently orbiting around the center of the galaxy. But because we're doing that independently, every so often we'll get just a little bit closer to some stars and they might seem to drift towards us then away from us. One star in particular, it's been calculated because we now have some very accurate measurements of what the stars are doing in our neighborhood. It's been calculated that on a time scale of 10 to the 6 here, 1 million years into the future, one star in particular is going to get very close to us. It's called Gliese 710, and it's going to come close and then go away again, simply from the way that we're both going round the center of the galaxy. This cloud on the left-hand side is a cloud of icy particles that surrounds our sun. There's our sun right in the middle of the so-called Oort cloud. The Oort cloud is a huge cloud of icy particles that we think is responsible, for instance, for comets that occasionally come into the solar system. If Gliese 710 comes into our solar system for quite a while, perhaps 1 million years or so, it'll disturb these icy particles out here in the extreme outer part of the solar system, and it will send some of these icy rocks in, and it will give us a whole load of comets raining down into the inner solar system, perhaps as many as a naked eye comet, a really bright, large comet, once every month for perhaps 1 million years. So instead of waiting for years for a comet to come along, there's going to be a whole train of them coming in for many hundreds of thousands of years. It's interesting to note that for a little while, this star will be inside the solar system. So our solar system will have our familiar sun at the center, but there will be a second star. For a while, we will have two suns in our solar system, just like various other planets, which I'm sure you recognize from Star Wars, for instance, like Tatooine. So yes, we will have two suns in our solar system for a little while, and then Gliese 710 will go away. Still on a time scale of 10 to the 6 years. This is an image of Meteor Crater, Arizona. Is this image there to tell us that these craters, these impacts of asteroids or comets, are expected once every 1 million years? Well, not quite, no. One thing we can note wasn't it really lucky that this asteroid just missed the visitor center? I mean, what a stroke of luck that was. If it had been any further to the left, it would have wiped it out completely. That's not right, it's there. It's there to remind us that on a timescale of 1 million years or so, we can expect any evidence of craters to be removed. In other words, on the surface of the Earth, we've probably had lots of impacts like this, but the old ones have simply been washed away by wind and rain and erosion because of the Earth's atmosphere. Of course, that doesn't happen on the moon, but there is actually something very similar that happens on the moon. The moon is continually being pulverized by a whole load of micrometeorites. They're only very small, but there are lots of them, and the moon isn't protected by an atmosphere, which means even things like the Apollo moon prints here from Aldrin, they won't last forever. They'll last a long time, but eventually the micrometeorites that are hitting the surface of the moon, pulverizing the surface rock, means that nothing will actually survive on the surface of the moon on this sort of time scale. In millions of years' time, the footprints will be gone. On a longer time scale, even the equipment that was left by man when we last stepped onto the moon, even that will eventually be pulverized and will be gone completely. On a time scale of 10 to the 7, we're now talking 10 million years into the future. That's an artist's impression of the Pioneer spacecraft, Pioneer 10 or Pioneer 11. They both have plaques on them that tell anybody that pick up this spacecraft where it came from. The plaque has a map of telling you where the Earth is and a little model of the solar system saying that this spacecraft came from the third rock from the sun. So if anybody picks this up, they can say, right, this spacecraft has come from that solar system, third planet out, and they know about Earth. However, on a timescale of 10 to the 7 years, 10 million years, remember, Pioneer and Voyager will be flying through solar systems every 10,000 years or so. So on this timescale, Pioneer will probably already have passed through hundreds of other solar systems. And maybe in one of those solar systems, somebody will pick up the Pioneer probe and have a look at it. But on timescales beyond 10 to the 7 years, this plaque will be eroded. Interstellar space is not empty. It's full of tiny dust particles. So if you travel for millions of years, that plaque will become pitted and eroded to the point where anybody picking it up will not be able to read the plaque. So if it's picked up in the first few million years, any extraterrestrial intelligence that looks at this will be able to figure out it came from Earth. Beyond 10 million years, they'll still be able to pick up the Pioneer spacecraft, but the plaque will make no sense whatsoever. It'll be so corroded they won't be able to read it, so they won't be able to tell where it came from. On a timescale of 100 million years into the future, we can ask what's going to happen within our solar system. For instance, what's going to happen to Saturn's rings? But perhaps before that, we should ask, where did Saturn's rings come from in the first place? The beautiful ring system around the planet Saturn. There are a number of moons around Saturn, and it's thought that maybe one of those moons was responsible for the ring system. If we look at that particular moon, Mimas, we might say to ourselves, perhaps you can just about hear Alec Guinness saying, that's no moon, that's a space station, because Mimas does indeed bear a striking resemblance to the Death Star here. Sorry? So it is thought that a simulation has said that if it is indeed one of the moons of Saturn that's responsible for the rings, a simulation was carried out in which one of the moons was effectively pulverized. So here's the planet Saturn without any rings. And a simulation has said if we pulverize the moon, then the simulation tells us that relatively quickly the debris from that moon ends up circulating around the orbit, forming a ring system. Notice how quickly the ring system actually forms. It only takes about 16 days or so. You might think this cloud of moon debris would simply go around the planet for a while, but actually it gets spread out into a ring system because all of the particles of debris are interacting with each other and producing the rings. Over a very long period of time, all of these particles will migrate slowly inwards towards the planet and produce the ring system that we all know and love. And that's, of course, what the Saturn ring system looks like at the moment. But if we predict what's going to happen into the future, all of the individual particles, all of the tiny ice particles in the ring system will continue to bump into each other, which means all of these are going to continue to migrate inwards, which means over time, all of these particles migrate inwards and eventually just rain down on the surface of the planet. So on a time scale of 10 to the 8 years or so, Saturn's rings will be gone. So anybody that likes looking through a telescope at Saturn, get in now, because in 100 million years or so, there will be no ring system to look at. Still on the same time scale, it's easy to think, because of orreries. Have we lost the audio? Can you still hear me okay? Yeah, okay. It's easy to think that on these timescales, we tend to think, because of orreries like this that show clockwork images, clockwork models of how the solar system works, we tend to think, well, if these things can predict where the planets are going to be next year or in 1,000 years, or if we wind them backwards, we can work out what was in the sky 2,000 years ago. In other words, we can try and answer the question, what was the Star of Bethlehem, for instance? We can do that over thousands of years, possibly even millions of years, but we can't do it over these timescales. On a timescale of 100 million years, we simply cannot calculate where things are going to be. Much like with the weather, we can calculate what the weather's going to be in a couple of days' time, but we can't predict what the weather is going to be in a month's time because weather is too chaotic. Well, ultimately, the solar system is the same. We can't calculate where planets are going to be 100 million years from now. We can't even calculate whether or not the planets in the solar system will be the same planets we have now. It might be that at some time in the future, Jupiter, being a very massive planet, might kick out some of the other planets in the solar system. So although these models look very pretty, they work very well over short timescales. They don't work over hundreds of millions of years, because ultimately the solar system is a chaotic system like the Earth's weather. Still on the same sort of timescale, 10 to the 8 years, 100 million years is roughly how long it takes the galaxy to rotate once. So our sun does one full rotation around the Milky Way in 100 million years. At the moment, we are sitting there, that's us, sitting in between a couple of spiral arms. The spiral arms are where the stars are most densely packed, most densely populated. And it's been calculated that on a timescale of 100 million years or so, we're going to move from a region which is relatively sparsely packed with stars. We're going to move into one of those spiral arms, which means we're going to have a lot more stars around us. So what's the consequence of having a lot more stellar neighbors in 100 million years? Apart from the fact the night sky is going to be even more spectacular because there's going to be more stars to look at. There are at least two consequences of being in a region of the galaxy which is much more populated with stars. One of them we've already sort of mentioned. When a star comes close to our solar system, it can disrupt all of the icy bodies in the cloud around our solar system, and it can give rise to a lot of asteroids and comets raining down into the inner solar system. And we can see that from the historical record. On timescales of hundreds of millions of years, we can look at how many species have become extinct on the planet, and we find spikes, quite a few spikes over a few 100 million years. So it's not regular as clockwork, but we know every 100 million years or so, there are mass extinctions on the planet. And we think that is quite probably because of asteroid or cometary impact, and we think those impacts are going to get more and more numerous as we go into one of these spiral arms. The most recent one on the right-hand side here is the KT boundary, the boundary between the Cretaceous and the Tertiary era. An impact at that point, that's the one that killed all the dinosaurs. And it gave us a chance to come, because we were, of course, just small mammals at the time, small furry rodents. We've now evolved into something slightly more, well, interesting than small furry rodents. So there are good things about mass extinctions, but it depends which list you're on, whether you're on the list of those that become extinct or those that survive. So this will certainly happen. There will be large rocks. Yes, this is an artist's impression, of course, but there will be large rocks hurtling towards the Earth when this happens. In this particular case, if you look at the left-hand side, it looks like Italy is in for a really bad day. But of course, it's not just Italy that will suffer. If something large hits the Earth, the entire Earth is going to suffer. Species will be exterminated. That is almost a certainty. The question is, will we be one of them? We've got plenty of time to sort of figure out what we intend to do, get Bruce Willis in, if necessary, to divert the asteroid or the comet, and hopefully survive what could otherwise be an extinction-level event. And there might be lots of them in 100 million years into the future. The second consequence of having lots of stellar neighbors is that at the moment, we've got very few stellar neighbors that are very massive. It's the very massive stars that end their life as a supernova, producing a lot of radiation, which could be a problem. At the moment, we haven't got many neighbors that are in that category. But in the future, we might have lots of neighbors which are massive enough to become supernova, and maybe that could become an issue. It's been calculated that supernova within about 100 light years of us, if they go off, it would be a danger to Earth. And if within 20 light years of Earth, the radiation produced at that relatively short distance could, in principle, be powerful enough to effectively sterilize the Earth. So we don't really want to have too many neighbors if we can get away with it. It's happened, it's definitely happened before. Supernova have gone off within 100 light years of us. We have a historical record that tells us that. there's a particular isotope that's produced called iron-60. It's a particular type of iron which doesn't exist naturally on Earth, but it exists when a star goes supernova. And iron-60 doesn't last very long. It only lasts for a few million years. And we found it in Earth sediments. It's not natural to Earth. It's only generated in supernova, and it only lasts millions of years. So if we see it in the Earth sediment, it must have arrived within the last few million or 10 million or 100 million years. It can't have been there since the Earth was formed. So we have evidence that supernova have gone off close enough to deposit that particular isotope of iron into our sediments. So it's happened before, could happen again. Still on the same sort of time scale, the Earth is still slowing down. It's going to be slowing down year after year after year for thousands, millions of years into the future. By the time we get to this point, tidal friction from the moon raising tides on the Earth, slowing the Earth down. The Earth slows down and the moon speeds up effectively. The slowdown of the Earth will be such that the moon is moving away from the Earth. It'll increase the size of the moon's orbit. That's for those that like this sort of thing, that's an exchange of angular momentum. The angular momentum of the Earth is being exchanged with the angular momentum of the moon. The Earth slows down, the moon gets further away. The Earth has now slowed down to the point that one day is 25 hours, not 24 hours. This might be a good point to decimalize the day and to give up on the idea that 24 is nicely divisible by 6 and 8 and 4 and all of these other numbers. The length of the day is 25 hours, and the distance from the Earth to the moon has increased to the point where it'll no longer be possible to have a total eclipse of the sun. At the moment, we have this wonderful accident, if you like, this coincidence that the apparent size of the disk of the moon is just big enough to cover the apparent size of the disk of the sun. So it is possible, under the right conditions, to get a total eclipse of the sun, where the sun is blocked out by the moon, but we're then treated to the site of the solar corona. That won't be possible from this point onwards, because the moon will be so far away, it'll never be large enough to cover the disk of the sun. At most, we will get either a partial eclipse or a so-called annular eclipse, where a ring of fire is left out around the disk of the moon, which is no longer big enough to cover the sun. But there's a more important consequence of the moon moving away from the Earth on these timescales. The moon has a stabilizing influence on the tilt of the Earth. The tilt of the Earth is currently 23.5 degrees. And as far as we can tell, it has been 23.5 degrees for a long, long, long time. The historical record indicates that this cartoon shows you what's going on. The change of tilt has only been about a degree or so over all of the records that we can see for the Earth. So the proximity of the moon has kept the Earth's tilt pretty much the same for many, many, many years. And that's made it nice and stable as far as seasons are concerned. But if the moon moves further away, that stabilizing influence is no longer there. If the moon is 25% further away, it might be that the tilt of the Earth decides to do some really wacky things and go to 0 or go to 90 degrees or flip-flop backwards and forwards. The seasons are going to be totally and utterly chaotic, or they could be at this point. So again, life is going to get very challenging in this sort of time when the moon moves away from the Earth. We're now 1 billion years into the future, and Voyager perhaps is still on its way through the galaxy. Remember, it's taken a few thousand years to go from our solar system to the next solar system, but on a timescale of 10 to the 9 years, things are going to change with the disk that it's carrying. Voyager itself will probably still be intact. Voyager is carrying messages from Earth on this gold disk, copper disk coated in gold, a phonograph. That will last 10 to the 9 years. Remember, the Pioneer plaque only lasted 10 million years. How come this one is going to last 100 times longer? Is it because they built it better? Well, not really, no. It's still flying through the interstellar medium, the space between stars, full of dust. It's still going to get corroded, but the disk has got a cover on it. and the cover is going to get pitted. The record inside, containing messages of welcome from Earth and some music, that is going to be protected. So the good news is the record will survive for 1 billion years. That's many, many, many solar systems that Voyager can pass through, and still this record will be intact. The downside, although the record will be protected, the cover will be smashed, and the cover contains the instructions for how to read the record. But let's hope that if Voyager is picked up by some civilization, by some extraterrestrial intelligence, maybe they're intelligent enough to figure out how to read the record, even though they don't have the instructions on the disk anymore. So for the first 1,000 solar systems it goes through, they'll be able to read the instructions. Beyond that, they'll have to figure it out for themselves. But Voyager will probably last for, of order, 1 billion years. And it's nice to think that our ambassador, our emissary, could, in principle, fly through thousands of solar systems. Maybe one day it will get picked up. What's happening to the Earth on the scale of 1 billion years into the future? Well, eventually our sun will change. Our sun has been shining quite happily for about 5 billion years, and it will continue shining quite happily for a few more billion years. It's got a lifetime of order 10 billion years or so. But it will start changing. In billions of years' time, it will start moving towards what we call a red giant phase, where it starts to swell up to a much larger star. Even before that happens, the luminosity of our sun will start to increase. It'll increase by 10% every billion years. So over a few billion years, the output of the sun will increase by 10%, 20%, 30%, which means the Earth is going to be pushed into a greenhouse effect. The surface of the Earth will become a relatively balmy 80 Celsius. That's a little difficult to live through. Essentially, the oceans will boil dry. Going underground isn't going to help much because it's going to be just as hot underground. If we want to survive, we'll probably have to leave the Earth until it's cooled off a bit and then come back later. The sun will expand, and it's been said that the sun will expand until the sun is the size of the Earth's orbit. Not the size of the Earth, the size of the Earth's orbit. In other words, it will expand until the surface of the sun touches the Earth. Now that doesn't sound very good. That could be a problem for us. But it's not absolutely sure. We're talking about the future, and we're talking about predictions based on calculations and what we understand in terms of the behavior of stars. And there are two schools of thought. One is that we're going to be engulfed by the sun, but other people say, yeah, but maybe not. Because yes, the sun is going to expand, and it's going to expand until it's similar to this circle here, the size of the Earth. None of this diagram, by the way, is to scale. But it's been pointed out that as the sun gets towards the end of its life, a lot of material is going to be lost from the sun. So-called solar wind is going to carry material away from the sun, so the sun is going to lose mass in the end of its life. If the sun loses mass, it's not pulling on the Earth as much. And if it's not pulling on the Earth as strongly, the orbit of the Earth will increase. Which means, if we sort of step through a little cartoon, as the sun gets bigger, the Earth actually moves away. So yes, the sun will end up approximately the size of the Earth's orbit. But once it's reached the Earth's orbit, the Earth isn't there anymore. The Earth will now be in a much larger orbit, perhaps out there where Mars is now. Maybe the Earth will survive. Very difficult to be absolutely sure about that. But let's be optimistic. Let's say, yes, the Earth survives that particular end of the sun's life. The sun will slough off its outer atmosphere, and what's left is the core of the sun, which is what we call a white dwarf. So now we're talking many billions of years into the future, 10 to the 10 years into the future. Bad news comes in threes. The first bad news is the sun will expand into a red giant. The second piece of bad news is that the Earth is going to lose its magnetic field. We've had a magnetic field for the last 4.5 billion years, and amongst other things, that magnetic field has protected us from cosmic radiation. The Earth's core is being kept molten not by the sun, but it's being kept molten by radioactive decay of elements in the middle of the Earth. They decay, release energy, that keeps the molten core molten. And a rotating molten core is a dynamo which generates the magnetic field which protects us from cosmic rays. Eventually, the radioactive decay in the core of the Earth will not be enough to keep it molten. The Earth's core will solidify. Once you've got a solid core, you no longer have a dynamo, so you no longer have a magnetic field. So that means we'll be exposed to radiation from the sun and radiation from the rest of the cosmos. I said bad news comes in threes. Okay, so we've got the sun expanding to a red giant. We've got the Earth losing its magnetic field. A third thing is going to happen on much the same time scale. We live in the Milky Way galaxy. Our neighbor is the Andromeda galaxy. The Andromeda galaxy is going to come our way. It's probably going to hit the Milky Way. At the moment, the Andromeda galaxy is visible with the naked eye as a small smudge of light. Over a few billion years, it's going to get closer and closer and closer, and eventually it's going to be so big you won't need a telephoto lens to have an image of it. You'll need a wide-angle lens to take a picture of it because it will fill basically the entire sky. The Andromeda galaxy and the Milky Way galaxy will probably pass through each other. That's not as cataclysmic as it sounds because the stars will not hit each other. The stars will not collide. They're too small, separated by too large a distance. When two galaxies pass through each other, one or two stars might collide with one or two stars, but most of the billions of stars won't. There will be tidal effects because the gravity of one galaxy is going to pull on stars from the other galaxy. So there's going to be a real mess for a billion years or so while the two galaxies pass through each other. But there's also going to be a riot of new star formation. Collisions of galaxies is not the end of life of galaxies. Au contraire, it's the beginning of life because when two galaxies collide, it triggers a whole load of new star formation. So that's going to happen. The galaxies will pass through each other and eventually they will settle down into one mega galaxy, which will be the merger of those two galaxies. Finally, the dance between the Earth and the Moon comes to an end in the sense that the Moon will continue to slow down the Earth, but on a timescale of 10 to the 11 years, the length of time it takes the Earth to turn once and the length of time it takes the Moon to go around the Earth, they will eventually synchronize. They will be the same. In other words, days get longer, months get shorter, and they eventually settle on the same thing. So not only will we find that one face of the Moon always faces the Earth, which is what we currently see. Whenever we look at the Moon, regardless of the phase, we always see the near side of the Moon. We never see the far side. Eventually, the same will be true of the Earth. If you were to step onto the Moon, you would only see one face of the Earth because one day is the same as 1 month. The Earth will be tidally locked to the Moon. I mean, this is what's been happening to the Moon for the many billions of years we've known it. Eventually, it'll happen the other way around. You could stand on one point of the Earth and you will always see the Moon in the sky. It will not change. It will not rise. It will not set. It'll always be there. Half of the Earth, you will never see the Moon. It will never rise above your horizon. So tidal locking is something that we know happens because we see it with other bodies in the solar system. Eventually, it's going to happen to us on this time scale. Notice the red square is now all the way over to the right. We are now 1 trillion years into the future, 1 million years into the future, 10 to the 12. We've already said that the Andromeda galaxy is going to crash into the Milky Way. Surrounding the Milky Way, there's lots of much smaller satellite galaxies. They're sort of dwarf galaxies, not particularly big compared to the Milky Way, compared to the Andromeda galaxy. The Milky Way is going to hoover all of those up. Effectively, they will all merge together. We've already said that the result of the Milky Way hitting Andromeda, or vice versa, those are going to merge together. The same is true of all of the galaxies in what we call the local group. The local group is just the name we give to all of the galaxies that are within a few million years of us. So eventually, Milky Way and Andromeda, M31, and the Triangulum galaxy, M33, they are all going to merge together into one huge galaxy. But what's going to happen to all of the other billions of galaxies that are out there, much further away? These galaxies are going to merge because they're relatively close and they're all pulling on each other through gravity. But what about the really distant galaxies? We live in a universe that's expanding, and because of that expansion, some of those galaxies are moving away from us. Even though some of those galaxies are moving away from us at faster than the speed of light, which sounds wrong but is actually true, even though that's the case, it is still possible to image these galaxies. From my front garden, I imaged a galaxy which is receding from us at twice the speed of light. It's really weird, but that is possible within the laws of physics because of the way the expansion of the universe works. On the right, there's a picture from the Hubble Space Telescope showing a tiny patch of sky in which there are thousands of galaxies. And that's a tiny patch of sky. That tells us that there are trillions of galaxies out in the observable universe. But if we wait long enough, in other words, this sort of time scale, 10 to the 12 years, the universe will have expanded so much, it'll actually be impossible to see those more distant galaxies. So at the moment, if we look out into the universe, we see stars in our own galaxy, and we see billions of other galaxies. But if we were to wait a while, or if you imagine in the future, what if a new civilization comes along and wants to know what is in the universe? If they build themselves the equivalent of a Hubble Space Telescope and look out into the universe, what will they see? They will see nothing other than the stars in their own galaxy. Doesn't matter how good their telescope is, they will not be able to see any galaxies beyond their own, or our own if they're in the Milky Way. So it's sobering to realize that we, at the moment, live in a time where it is possible for us to see billions, if not trillions, of galaxies in our observable universe. But if we were to wait a while, that will not be possible. And an advanced civilization may come to the conclusion that the entire universe is just their little island galaxy, because that's all they're capable of seeing. And they will be totally unaware of the fact that the universe is actually full of other objects. I said that it took 3 minutes to make all of the hydrogen in the universe. But after a few trillion years, it might only take 3 minutes to make it all, but stars are now taking that hydrogen and converting it to other elements, converting the hydrogen to helium and carbon and nitrogen and oxygen and calcium and phosphorus and silicon. It only took 3 minutes to make everything, but after trillions of years, the hydrogen is starting to run out. There's only a finite amount of it in every cubic light year of the universe. There's only so much hydrogen. And if you have stars eating it up and making other elements, eventually it's going to run out. As an aside, some people have said, is it not possible that you can actually make stars out of something else? Is it not possible to make stars out of heavier elements? Some people have said maybe it is. Maybe you don't need hydrogen. Maybe you can start with a heavier element, a heavier gas, and start to make stars. Some theorists have said, well, there's no evidence for it, but I reckon it's possible to make a star with nuclear reactions at the core, but surface temperatures that are much lower than the sort of stars we see around us today. Not thousands of Kelvin, thousands of degrees, but maybe hundreds of degrees, maybe as low as 273 Kelvin or 0 Celsius. Maybe it's possible to think about stars being made with nuclear reactions at the core, but ice in the atmosphere. Frozen stars. And for those of you who think of the Disney version of Frozen, that would be a Disney version of a frozen star. That's not what I'm talking about. So if that's what you've got in your head, let it go, because what I'm talking about is something rather different. Nuclear reactions with ice in the atmosphere. Some people say that's possible, some people say baloney. No, you need hydrogen to make stars. So we've now stepped up. We are coming towards the end of the talk, and so I don't spend the next 3 or 4 hours giving you the rest of it. we're going to change the scale along the top. Instead of each box being 10 times further into the future, each box is now 1,000,000 times further into the future. So we're starting from beyond 1 trillion years. We said the Big Bang made all of the hydrogen in 3 minutes, but after trillions of years, it's running out. So if it's running out, what's going to happen? Stars might live for a long time. Some stars might live for billions of years, like our sun, or some stars might live for trillions of years. But they don't last forever. So what does that mean? Unfortunately, we have lost the music in the background. But one by one, the stars will go out. And there's no more hydrogen to make new stars. So on this timescale, the age of starlight is going to come to an end. It will be on timescales greater than 1 trillion years, but less than the number in the red rectangle. On this timescale, stars will no longer be shining. The stars will still be there. They will be dead stars, zombie stars, if you like, still orbiting in their galaxies. There will be white dwarfs, neutron stars, and black holes. White dwarfs start off illuminating. They will start off white, but only because they're hot. They will cool down, and eventually white dwarfs will no longer be white. So all of these objects will eventually become dark, and there will be no more stars shining in the sky. There are no nuclear reactions going on. So even in a white dwarf is just a lump of whatever elements have been made, probably carbon and a few other elements. And so it'll start off white hot, but eventually it'll go dark, and a white dwarf will just end up as basically a black dwarf, just a lump of black carbon. Some stars, quite a few of them I guess, will be eaten by the black hole at the center of the galaxy. Every galaxy, as far as we know, has got a really big so-called supermassive black hole at its core. And that supermassive black hole is going to eat up a lot of the stars that are left in the Milky Way, and presumably every other galaxy in the universe. I said earlier that galaxies merge, like the Andromeda galaxy is going to merge with the Milky Way. When they do, after a little while, the black hole at the center of Andromeda and the black hole at the center of the Milky Way, they will end up merging as well. And that will happen all over the universe. Black holes will merge together. They might be quite large already, but if a lot of galaxies merge together, the black holes could grow from millions of times the mass of our sun to billions of times the mass of our sun, perhaps even trillions of times the mass of our sun. There's no real limit to how large they can get. Perhaps that would be the limit, many trillions of times the mass of our sun. But even black holes don't last forever. Black holes may sound like, once you've made one, that nothing's going to happen other than it eats up anything around it. But no, black holes evaporate, as far as we know. Stephen Hawking hypothesized that black holes evaporate, and most scientists seem to agree with him. It's a quantum mechanical event. It's a quantum mechanical thing, which I'm not going to go into the details of, but it's the consequence of the way quantum mechanics works, the mechanics of how things work on a very small scale. If we think about what's going on just outside the event horizon of a black hole, so it's not radiation coming from inside the black hole, but we think the event horizon will radiate and the black hole will evaporate. But it is a very, very, very slow process, which is why the red rectangle has already crept quite a long way over to the right-hand side of the screen. The black hole evaporates. Hawking has predicted that the amount of radiation coming from a black hole depends on its size. If it's really big, the radiation is not that much. As the black hole gets smaller and smaller and smaller and smaller, the radiation goes up and up and up and up. So as it gets to the end of its life, as the evaporation continues, as the black hole gets really small, it will suddenly end its life in a flash of radiation. And all of the matter of the black hole is converted to radiation. even the big black holes, even the supermassive black holes, the ones that are trillions of times bigger than the sun, even they will evaporate eventually. But that process will take much, much, much longer than the smaller black holes, because the large ones radiate so little. But it will happen. So I've now effectively got the end of that timeline. So have we reached the end of time? All matter in the universe, all the stars have stopped shining. We've ended up with white dwarfs which have evaporated. We've ended up with black holes which have merged together and then evaporated. All of the matter has disappeared. We're just left with some radiation. The universe will continue to expand, but there is no matter left. After a time period of approximately 1 to the power 100, that's a googol, not that Google. That Google is a misspelling, it is believed. When they set up that company, they were intending the company to be named that, but somebody misspelt it. So 10 to the power 100 is a googol. And after 1 googol years, it has been calculated every black hole, all matter in the universe will have gone. That's how long it takes the biggest black hole that we can conceive of to evaporate. And I don't normally put zeros on these presentations, but let's just remind ourselves how silly a number is 10 to the power 100. It's an awful lot of years. After this time period of 1 googol years, nothing happens. Nothing of any consequence happens, and therefore time, you could argue, becomes absolutely meaningless. Because if you have a universe full of radiation and the universe continues to expand, if there's no matter in the universe, then nothing actually happens. And this is how silly the number is. That's a googol years. 10,000 million. I'm not going to finish it. You can do it yourself. An exercise for later. It's a silly number, but just because it's a silly number doesn't mean you can't do the calculations and figure out that that's how long it would take for the biggest black hole to evaporate. So you could argue that's not the end of time, but it's as close as makes no difference, because nothing interesting happens after this point. The universe just continues to expand. How do we finish a talk like this? Well, you could say eternity is a very long time, especially towards the end. That was a quote from Woody Allen. But I prefer the cartoon XKCD, which is a cartoon which has some very insightful quotes occasionally. They said that if you want to put a human spin on the universe, this is the way to do it. A human, you could say, is a system for converting dust billions of years ago into dust billions of years from now via a very roundabout process which involves checking email a lot. It's one way of thinking of it. So the universe is going to come to an end as far as we can tell, according to our best estimate of what we see around us today. But let me finish on a slightly more upbeat note to finish the hour. You could say we live in a golden age. The sun is middle-aged, the sun is stable, the sun is well-behaved, has been for 5 billion years and will be for quite a few billion years to come. The moon is at just the right distance to stabilize the Earth's axis and hence stabilize the seasons, and as a little bonus, it also gives us a disk that's just right the size to occult the sun and give us a total eclipse of the sun if you want to go globe-trotting around the Earth to see one. Thanks to evolution, we are able to explore the universe and discover the universe and, to some extent, understand the universe. And we can do that by sending space probes out to our immediate neighbors to explore other planets. We can also build telescopes that allow us to see trillions of galaxies billions of light years away and get a better understanding of the universe in which we live. In the very early universe, mankind could not have existed. We needed generations of stars to process hydrogen into helium and lithium and beryllium and boron and carbon and nitrogen and oxygen and calcium and phosphorus and iron and all the other elements that make us us. And we've just seen that in the future, the universe is going to be very dark and very boring. So you could say the best time to exist is now. Thank you.